Assalamualaikum dan salam sejahtera. So today we continue our lecture about ideal flow, and today we are going to see the usage of our the usage of the basic flow patterns. Okay, as I explained previously. So for example, we have a square box here, and this square box move from this point to this point. And then at this point, the square box is now transferred like this one. The shape is also deformed and become like this one. So then to express this deformation, so it is easy for us to explain it step by step. So as I explained yesterday, so we just imagine the transformation on x-axis, so it will become like this. And then the transformation on y-axis, so it will become like this one. And then the transformation of the both sides, so it turns the square box. So you give shear force like this one, and then it can change into this shape. Okay, so means that to imagine or to represent the transformation of this box to this shape means that it is okay for us to combine these three deformation. So mean the deformation on x-axis, and then the deformation on y-axis, and finally the shear deformation that occur on that shape. So now, so by using this basic idea, we believe that by the combination of a few basic flow patterns, we could reflect the complicated example. We could solve a complicated problems. Okay, now we will see a few combination by using our basic flow pattern that we learned yesterday. So first is the combination of, okay, so we have a linear, we have source, we have sink, and we have vortex. So now we will see about the linear and source. So, and then we will see about what happened if source merge with sink, and what happened if these three, linear, sink, and source, and then what happened to linear, sink, source, and vortex. So this is the basic one that at least you must know. So the end of these topics, or the major application for this one, is the usage of CFD. Because CFD, computational fluid dynamics, it means that you need to do the simulation of complicated application, complicated movement, or complicated phenomenon. So to simulate that, you must imagine from the very basic flow, and then you do the combination, and then by that combination you will give any extra parameter. So, and then you could verify, you need to verify with the experimental works or the basic calculation. And then if your simulation is correct, means that you could simulate for extra complicated, more complicated problems. So this is the flow path at all, means the flow chart of computational fluid dynamics. But now, because normally in computational fluid dynamics and so on and so forth, you will use coding, and your computer will help you to calculate all the calculation, and means that the CFD is not possible to be tested in class. Okay, because we have final exam. So, but this is the very basic calculation, the very basic idea to simulate the real phenomenon into the mathematical expression. Okay, so means that you must calculate, you must know how to calculate this, you must know how to reflect all the movement into the mathematical expression. Okay, first we go for the simple one. Okay, so we try to combine linear and source. And when we combine linear and source, we will have one phenomenon which called a Rankine half body. So we will see about this. So this is the overall idea of these topics. So first we want to know what happens if we have linear and we merge it with source, and it will give us one shape, and we call that shape is Rankine half body. Okay, let's say we have this one. Okay. Okay, I'm sorry. So we continue our discussion here. Okay, this is actually what happened if we merge linear and source. Okay, what you should understand when we combining linear and source is, okay, linear here will reflect a linear flow. So we could draw a linear flow like this one. So in this case, we always take linear flow, which is from right to the left, as our representative linear flow. So selalunya di dalam kebanyakan buku, dia akan beri awak linear flow dari kanan ke kiri. Okey, mengapa? Kita akan lihat apa nama tu di akhir perbincangan ini, awak akan dapat idea kenapa selalunya buku akan beri daripada kanan ke kiri. Okey, tapi awak ingat, normally kita akan ambil linear flow sebagai satu aliran yang bergerak di atas garis lurus. Okey, apa nama tu daripada kanan ke kiri. Dan normally we will take the linear flow as a horizontal flow. So because previously when we discussed about the linear flow, you may have linear flow like this one. So means that if we take linear flow like this one, means that you need to take both, mean the effect of U and the effect of V, because you purposely you purposely have y-axis. So if you take linear flow as a horizontal flow like this, so means now you are purposely neglecting the y-axis, because you only show that this flow is actually on x-axis, so mean that the influence or the effect of y-axis can be ignored actually. Okay, so I hope you could understand why we take linear flow as a horizontal flow like this one. Okay, because it is everything to ease our calculation, to make our calculation simple. So and then, so this is actually the final after linear flow combined with source. So what happened before that? I hope you could imagine that, for example, so we know that source is flow that comes out from one source and it flow on the radial axis. And linear flow is a straight line like this one, and then you start to imagine is if this molecule and this molecule meet each other, so they will collide. So maksudnya jika ada molekul daripada linear flow di sebelah kanan bertemu dengan molekul daripada source flow dari sebelah kiri, mereka akan bertembung di seperti ini. Okay, awak just imagine like this one. And then You need to believe that we are calculating a real one, a real thing. So means that when two masses, dua jisim yang dua jirim yang mempunyai jisim, two molecule which has mass, so mass need to be conserved. Mean that mass cannot be disappeared in split second. So mass must be there. Okay, kita belajar tentang keabadian jisim, kita mengatakan bahawa walaupun berlaku pelanggaran dan sebagainya, dua molekul ini tidak boleh hilang. So dia kena tetap juga bergerak. Okay, tetapi selalunya kalau berlaku pelanggaran di dalam garis lurus yang ini, selalunya kita akan membuat anggapan bahawa molekul akan terberhenti untuk seketika. Itu sebab pada titik ini kita akan namakan stagnation point. Kerana kita beranggapan apabila dua molekul berlanggar, molekul itu pada satu masa dia akan terberhenti seketika, kemudian barulah ia menyambung pergerakan. Kerana apa dia perlu menyambung pergerakan? Kerana ia perlu mengekalkan dengan idea conservation of mass. So maksudnya molekul tidak boleh hilang begitu saja, dia akan pergi somewhere else. Okay. So and then apa yang berlaku di sini, okay, kita berhenti dulu setelah dia berlanggar. Okay, kemudian kita dapati bahawa molekul di sini akan bergerak juga, tetapi pelanggaran dengan molekul ini akan berlaku ke belakang sikit, maknanya lebih ke kiri. Kerana apa? Kerana had laju ataupun pergerakan molekul untuk source adalah dalam bentuk radial. Oleh itu sekiranya contoh yang paling senang di sinilah. So sekiranya ia mempunyai had laju yang sama dengan yang had laju horizontal ini, jarak yang dirasai atau jarak pelanggaran berlaku akan lebih ke kiri. Okey, so boleh nampak So jadi dengan alasan itu kita dapati bahawa apabila linear dan source bertemu, so ini adalah center of source, when these two molecule collide, so it start to move somewhere else. So where these two molecules go, so it will go and it will flow on this path. Okay, so saya terangkan sekali lagi kerana awak perlu faham yang ini, kerana ini adalah key turning point untuk kita memahami how basic flow pattern combine with each other. Okay. So jadi saya harap awak dapat imagine kita ada linear flow di sini, molekul akan bertemu dengan molekul daripada source, dan saya katakan bahawa molekul kita akan kekal kerana conservation of mass. Oleh itu apa yang berlaku, ia akan bergerak ke arah yang lain. So ke mana arah dia bergerak? Dia akan bergerak di atas garisan biru ini. Kerana apa? Kerana pelanggaran yang lain, kerana yang lain, molekul yang lain, kita kata di sini, so dia tidak dapat meneruskan pergerakan, so dia akan terbengkok, yang ini pun dah terbengkok dan sebagainya. Okay. So and then di sini kita kata mereka pun molekul di sini tidak akan boleh mendebusi laluan ini. So apa yang berlaku, ia akan membengkokkan dirinya seperti ini. Okey, so boleh So sampai sini ada kekeliruan ke?
Okey, saya tak ada.
Okey, so saya harap awak dapat imagine. Perkara ini sebenarnya awak boleh buat dengan mudah. Contohnya apa yang awak boleh buat ialah awak pergi dekat bilik air ke, ataupun jika ada hose, ada hose di car porch awak atau hose di mana-mana sahaja, it is okay. Okay. So apa yang boleh awak buat ialah awak dapatkan dua hose, maksudnya dua hose air. Satu hose air awak letakkan seperti ini, supaya air itu keluar dalam bentuk linear. Okay, boleh nampak? Okay, boleh imagine So maknanya that is the linear flow. Kemudian awak perlu untuk create source flow. So macam mana nak buat source flow? Awak dapatkan lagi satu hose. Okay. Awak dapatkan satu hose, awak letak secara vertikal supaya air jatuh ke bawah dan terserak ke seluruh arah. Okay, boleh imagine ke? Okay, so setelah awak buat itu, awak akan dapati bahawa akan terbentuk bentuk seperti ini. Dan air akan tetap mengalir ke sebelah ini. Okay, tetapi awak akan nampak akan ada ombak yang akan membentuk ini. So, sementara air daripada sos yang di tengah ini, okay, dia akan bergerak juga ke bawah. So, awak dapati bahawa tidak ada air yang cross the borderline. Okay. Okay, so boleh imagine sampai sini?
Boleh,
Boleh,
sir.
Doktor.
Boleh, sir.
Okay, so balik you try lah membazir air sikit. So, awak boleh test, at least awak dapat reflect bahawa apa yang kita belajar di sini adalah boleh dibuktikan secara fizikal. Okay, so means that awak kena imagine bahawa apabila linear flow bertemu dengan source, dia akan membentuk satu bentuk ini. Okay. So, perkara ini telah dikaji oleh seorang saintis bernama Rankine. Rankine ni nama saintis. So, ia telah dikaji oleh seorang saintis bernama Rankine, dan Rankine mendapati bahawa bentuk ini sebenarnya unik. Unik tu membawa maksud ia mempunyai beberapa ciri. Pertama, kita dapati bahawa garisan ini sebenarnya adalah borderline yang membezakan di antara aliran di dalam source dan juga aliran linear flow yang di luar. Membawa maksud bahawa aliran linear flow yang di luar tidak akan masuk ke dalam dan tidak akan ada aliran source yang akan melompat keluar. Okay. Itu satu. Kedua, kita Rankine membuat pemerhatian dan membuat kesimpulan bahawa di sini akan berlaku satu keadaan di mana molekul sebenarnya berlanggar dan berhenti seketika sebelum ia bergerak ke arah yang lain. Oleh itu, pada titik ini dinyatakan sebagai stagnation point. Ini antara yang awak kena ingat. Okey, so kemudian satu perkara lagi yang dinyatakan oleh Rankine ialah sekiranya kita menggantikan kawasan ini, maknanya kita menggantikan kawasan ini dengan solid object. Okay, boleh faham if we replace this area with solid object. Solid object, we will find that all the properties is remain the same. So maksudnya walaupun pada dasarnya kita mula-mula kita gunakan source, kita merge dengan linear flow, and then kita dapat bentuk ini. So kemudian sekiranya bentuk ini kita gantikan dengan solid, maknanya awak letak papan ke dan sebagainya yang berbentuk ini, so you will found that all the parameters. So parameter tu apa? Maksudnya had laju linear flow yang lalu di sini masih lagi sama. Okay, awak pun boleh faham when velocity change, so the pressure will change. So mean that here the velocity direction is change, means that the pressure at this point and at this point may be different. So the parameter means the velocity condition and also the pressure condition that occur on this shape, okay, is remain the same. Okay, walaupun kita gantikan source tersebut dengan solid object. Jadi yang paling mudah, apa application yang reflect tentang perkara ini? So the application that maybe use this idea is our evaluation on aerofoil. So for example, if we have aerofoil like this one, so how we need to express the shape of aerofoil in mathematics? Might be the simplest one is by replacing the shape of aerofoil here by source flow like this one. Okay, ini very basic lah, walaupun dia tidak akan menjadi aerofoil lah, dia akan ada pertambahan perkara lain. Okay, tapi maksudnya awak boleh dapat permulaan untuk mengira sesuatu kita boleh adalah digerakkan dengan cara combination of basic flow patterns. Okay. So kemudian kenapa dinamakan Rankine half body? Okay, it is because Rankine found that this width is actually growing. It's become bigger and bigger, and it will never intersect at one point. So means that katakan kita ada satu keadaan yang panjang, so ini adalah source katakan, dan ini adalah linear, so dia akan membentuk bentuk macam gini kan. Tetapi Rankine mendapati bahawa bentuk ini semakin lama semakin membesar. So oleh kerana bentuk ini tidak akan bercantum, it will never intersect each other. So Rankine call it as half body, because this body will remain half of them only. Dia hanya half saja, separuh saja yang terhasil. Oleh itu dikatakan Rankine half body. Okay. So means that for general explanation, I hope you could understand what basic shape occur when we merge, we combine linear flow and source flow. Okay. Okay, so it is called as half okay, it is called as Rankine half body. Okay, and then because the sumber, the source here, okay, so it's reflect as a solid body, satu badan tegak as a solid body, and it doesn't have end of the shape. So maksudnya dia tidak ada penghujung. So oleh itu Rankine menafsirkan dia sebagai Rankine half body. Okay, seterusnya. Okay, seterusnya I would like to introduce you a few very, very important point and definition that you should know before we could evaluate this one. Okay, so we have a linear flow here, so we have a source flow here, and the combination of linear and source flow will create a Psi combination. So this is the Psi combination. So a Psi combination is depend on the definition. You should know the definition. So the definition of a combination is the combination of source and linear. So where is the combination occur? So the combination occur when this molecule merge with this molecule. When it collide, so it will stop for a while. So and then it will move on this blue line. That's why this line only is called as Psi combination. So awak kena tahu bahawa yang dikatakan Psi combination ialah apabila parameter source ini bertemu dengan linear flow dan ia membentuk nilai ini. Okay. So ini yang dikatakan Psi combination di dalam topik kita. So in this topic, it is okay for you just to imagine that the Psi combination is actually the combination of source and linear, which is shown as this line. Okay. Ini dalam peringkat awak saja. Okay. Kerana kalau dalam peringkat yang lebih tinggi, sebenarnya yang atas ini pun adalah combination. Okay. So, tetapi combination ini dibuat bukanlah simply dengan menggabungkan source dan linear, kerana awak perlu tambah elemen lain. Kerana ia sebenarnya, kalau awak, ini linear, kalau awak tidak menggabungkan dengan apa-apa parameter, linear akan tetap bergerak terus. So dia akan langgar yang ini. So jadi awak kena ubah juga parameter, so awak kena masukkan linear, and then awak akan masukkan dengan nilai yang lain. So nilai yang lain ini kita tidak bincangkan di dalam calculation kita. Di dalam CFD mereka akan dapat. Kerana idea lain yang kita gunakan di sini ialah so kita kata awak pun faham linear flow di sini sebenarnya adalah stream function, dan for sure kita ada velocity potential. So velocity potential, as we discussed previously, it is an imaginary line and it must be perpendicular to the linear flow. So imagine that first we have something like this, and then we have like this, we have like this, and so on and so forth. Okay. So and then, so the Psi combination will give us exactly will give us this blue line. Okay. So, and then from this blue line, we could calculate what is the, okay, let's say from here. So we have a velocity potential line. We could calculate the volume here, the mass, for example. And the mass can be estimated with certain velocity because the velocity of linear flow here is already known. So we could estimate, so what is the shape of the second step here. So because the mass is constant, so and then what is the mass of this one, and according to the mass we could imagine the shape. Okay, boleh faham ke? Awak boleh imagine ke apa yang berlaku sebenarnya?
Boleh sir, boleh.
So far okay sir.
Okay, so jadi saya awak faham. Ini adalah basic idea macam mana kita nak imagine the formation of streamline on certain object. Jadi kita kena dapatkan yang paling utama sebenarnya adalah Psi Combination. That's why in this topic we are focusing on Psi Combination. Because the rest here, yang another line kat sini, kita boleh dapatkan, apa nama tu, kita boleh dapatkan dengan pelbagai jenis pengiraan. Okay, boleh dapat So yang itu yang saya harap awak dapat faham. Sebab ini adalah kita kata first time kita tengok combination. Kerana supaya ini kita akan melihat banyak lagi combination. Jadi saya harap awak dapat imagine. Okay, so apa yang perlu awak beberapa faham ialah yang dimaksudkan dengan Psi Combination ini actually adalah garisan ini sahaja. Okay, so boleh. So kemudian di hadapan ini, okay, kita akan nyatakan sebagai stagnation point. So kita akan tandakan dengan simbol S. Okay, stagnation point. So kemudian kita kata kita akan ada pertembungan dua koordinat. We will have two coordinate right now. In linear flow, we will evaluate in X and Y. So and then in source flow here, we will evaluate by using the polar coordinate. So means we will describe as R and theta. So at this moment, if you have this situation, you need to choose one of them. Means whether you use all in Cartesian coordinate or you use all in polar coordinate. That's why in linear here, normally linear will change. We will change linear coordinates into polar coordinates. That's why if you have a side of linear here as uy, okay, so you need to change as u r sine theta because it is to merge, because we are now merging this one, so you need to change. Okay, so awak ada 1 kilogram dan 100 gram. So awak tak boleh nak simply campur, so awak kena tukar 100 gram kepada kilogram juga. Okay, boleh dapat something like that. Okay, so itu another thing that you should know. Sometimes maybe you confuse which parameter that you want to use, which coordinate. Okay. Okay, now you know about the stagnation point, you know about the Psi combination, and finally we have another two parameter. So in polar coordinate, the coordinate is shown by r and theta. So what is the meaning of r here? So the r here is the distance from the source to the Psi combination. So means that we have R1 here, we have R2, we have R3, R4, R5, and so on and so forth. Okay, boleh imagine because the basic definition of R is the radial length. So in this situation, this is actually the length of the radius, but it is stopped. Okay, it is stopped until the Psi combination here. So maknanya ia adalah jarak, distance from the source flow, center of source flow to the Psi combination. So awak kena imagine bahawa in this combination, the value of R will varies. Dia akan berubah-ubah kerana bentuknya bukanlah bentuk bulat. Okay, yang itu awak kena faham juga. So nilai R akan berubah. So another thing that you should understand here is R, again, R is the distance from the source flow here to Psi combination. R is not equal to y-axis. jangan silap faham. Kebanyakan pelajar dia akan anggap R adalah y-axis. No, R is not y-axis. Y-axis is the distance, is the vertical distance. Okay. Okay, because for half body Rankine, for Rankine half body here, we have another parameter which called the y asymptote. So the y asymptote here is actually the distance. Okay, you should know the definition. The y asymptote here is the definition from the center line here. From the center line to psi combination on y-axis. Means it is a vertical distance. A vertical distance mean y-axis here from the center line to the psi combination. Okay, saya harap awak dapat melihat gambar rajah dan dapat mengingati takrifan-takrifan ini. Okay, as shown like this one. Okay, we look to the notes. Okay, S here is the stagnation point, and you know, stagnant means there are no movement. So we assume that velocity at stagnation point is equal to 0. Any velocity. So means that if you are talking about Cartesian coordinate, so mean that the u and the v is 0. And in polar coordinate, ur and u theta is also equal to 0. So mean in stagnation point, there are no movement. But this happened for a while. So they just collide, they stop for a while, and then they need to go to another path. Okay. So and then as I said, the value of R1 is not necessarily equal to R2 because the R here is different. Okay. So and then the y asymptote here is the vertical distance, mean distance for y-axis, start from y equal to 0, mean from the center line here to the psi combination line. Okay, psi combination. Okay, and then if the question asks you to calculate what is the width of Rankine half body, so you could calculate the width of Rankine half body is 2 times the value of y asymptote. As you could imagine here, the width here is actually from here to here, so mean it is y asymptote times 2. Okay, I hope you could get a clear picture about this one, because in this topic we are regularly will use terms of psi combination and sometimes y asymptote and stagnation point. Okay, ni nota. Okay, now we will go to the mathematical approach. Okay, so we need to calculate what is stream function. Okay, the stream function here means the combination stream function. So this stream function depends on the situation. It is not necessarily linear and source. It's depend on the question. If question asks linear, source, and vortex, so you need to do the combination of that condition. Okay, first we are learning about linear plus source. So how to get our psi combination? Okay, back to the definition. Psi here is actually equal to flow rate. Okay, as I said previously, so flow rate is a scalar, so means the direction of flow rate is actually not counted. Means you may add all the value of psi of stream function to get this combination stream function. So the idea is simple. If you have two pipes here with Q1 and Q2, so you will get the resultant here as Q1 plus Q2. There are no Q1 square plus Q2 square, square root, and so on. So that is for vector. Okay, please bear in mind. Okay, so means that the psi combination here, how to get the psi combination here, you need to add all the stream function. So we have two of them. So we write linear stream function here plus the source stream function here. So linear, when it moves from right to the left, So, you know, we have an X axis here, Y axis here. So if the motion is from right to the left, so it will reflect a negative direction. So we have a negative direction here, negative uy, and source. So we will give the basic flow pattern. So the stream function for source is m theta over 2 pi. So, and then as I said, in this stage, we have two coordinates, linear and Cartesian and polar coordinates. So what we need to do, we change one of them. So in this situation, we change the Cartesian coordinate into the polar coordinate. So we have negative UR sine theta plus m theta over 2 pi. So we call this a Psi combination. So and then, okay. So this is another important step that you need to understand, okay? Because many students sometimes they neglect, they forget to do this step. We get UR psi combination is equal to negative UR sine theta plus m theta over 2 pi. So here we need to determine what is the value of psi combination, because you cannot let psi combination equal to 0 without any verification. Okay, you need to you need to calculate to determine, to prove that psi combination is equal to what numbers. Okay, normally researcher will try to rearrange the coordinates and so on and so forth to have psi combination equal to 0, but not all the situation you will get psi combination equal to 0. Okay, so the idea is simple. Okay, we go back to the graph here. Okay, so the idea is simple. It is actually when now we are represent our real situation here by using a mathematical expression. So what we get here, the psi combination here is actually a graph. Awak hanya imagine bahawa psi combination ini adalah graph. So sekiranya di dalam graf ini awak menghadapi masalah y sama dengan katakan a x kuasa 2 campur bx campur c, so you have an unknown equation. So what how to get the unknown equation? You use any coordinates on the line, substitute into the equation, then you could solve the problem. Betul kan? Awak boleh imagine ke? So, cara untuk kita menyelesaikan permasalahan yang melibatkan graf. So, idea dia adalah rule of thumb, awak guna mana-mana coordinates yang ada di dalam graf, masukkan di dalam equation ataupun masukkan dalam equation graph tersebut, awak boleh menyelesaikan masalah. So, we use this idea. So, what we need to do is, so we need to substitute one coordinate, okay, into this equation, then we could determine whether psi combination is equal to 0 or not. Okay, and then, okay, we have this kind, okay, we have a stagnation point here, so and then this is the center of source SR, okay, this is an R, okay, a small r here, okay, so in this situation, so it is worth for us to take the coordinate of stagnation point, because in stagnation point we could determine as r theta, okay, and the value of theta is equal to 0, so it's become r and 0. Why it's become why this point is equal to 0? Because we this is source, okay, and source here will become the origin, and then this is the stagnation point, and normally 0 angle is start from this axis. So here is 45, so here is 90, and so on so forth. So here is 300 degree, for example. So mean it start from this line, okay, so means that the value of S here, the coordinate is R and 0. So as stated here, So we substitute the value of stagnation point, the coordinate of stagnation point. So it is equal to r and 0. And then when we substitute the value of r and 0, so r is remain as r, but sine 0 and m0 here will give us the value of 0. So now we could say that psi combination is equal to negative ur sine theta plus m theta over 2 pi, and it is equal to 0. Okay. So this is the final equation that we should use in our next calculation. Okay. So and then so this is beyond our syllabus. Actually, okay. So we have this one which is psi equal to 0. So this is psi equal to 0. And then here, actually, we have another psi. So let's say, but for this is psi is not equal to 0. This is also not equal to 0. Okay, so it is depend on the mass flow rate and so on and so forth. So for example, here is psi equal to 10. Here is psi equal to 20, for example. So it can have occur like that. Because the basic idea is psi equal to 0 here is actually the bottom line or the reference line that we created to start our calculation based on continuity later on to determine what is the line for the second, third, fourth stream line and so on and so forth. So that is the idea, but in your syllabus we are not calculating this one. Okay, we are just focusing on the psi combination line, which is here. Okay. So and then we try to calculate what is the velocity component. So please remember Cochileman equation. I will go a little bit faster here because you already know about Cochileman equation and so on. So because we are dealing with polar coordinate, so means that we have UR and we have U theta. So we refer to Cochileman equation for Cartesian coordinate. So we have UR d psi r d theta. And then we differentiate the psi combination here. Okay, here, please bear in mind, you could write like this. You have a d psi over d theta. And the psi here is actually the psi combination because we are focusing on the psi combination line. So you need to understand that this psi is actually psi combination, and it also can be write as d theta psi combination. So mean you substitute the psi combination that you get here, so which is this value. Okay, so you just substitute in these terms. So finally you will get the UR is equal m over 2 pi r minus u cos theta. So this is the value of UR. So and then we calculate the value of u theta. So from the Cochileman equation, we get this one, and I think you already know what to do. So finally, you will get u theta is equal u sine theta. So this is the velocity. So the problem is now, could you imagine what actually happened? Can you imagine what direction or how this component velocity act? Okay, the idea is simple. So we have a half body Rankine like this one. So let's say this is the origin, and let's say we are evaluating on this point. So let's say we have a curve like this, okay, and then we have a molecule here. So as you see that the radial axis is like this. So means that the UR here is the velocity something on this direction. And then theta is actually the direction reflect the tangent of this one. So it's maybe show like this one. So this is the theta. So and then if you get this one, so you will have a resultant velocity which is reflect to this one. So this is the resultant velocity that actually occur in this for this point. Okay, so might be my calculation, my drawing is not to scale, so might be you look a little bit weird, but at least you understand that what is the meaning of UR and what is the meaning of U theta. So at least it is about one molecule here. So actually it's moved. It had a component of radius here. It has a component of theta here. So and then finally it need to move along this line. Okay. So maybe it's here is the velocity is quite short, for example. Okay, and then it's not easy to okay, let's say okay, you have a molecule here. So maybe this is the UR is quite small, and then maybe you have a tangent big one, and then if you have, so you have the velocity like this one. Okay, something like this. Okay, if you want to see the real one. Okay, so means that here the most important is you know what is Psi combination, and you know how to get your velocity component from your Psi combination, and you could imagine what actually happened. So where is the UR, where is the U theta here, and then what is the resultant velocity.